Now let's see if we can understand the implications of this delta t prime equals delta t over 1 minus v squared over c squared. Delta t prime is the time that we measure between beeps or round trips of the light beam. Delta t is the time as measured from within the lab that's passing by us at velocity v. Okay, if velocity v is 0, as we saw, then the delta t prime will just be equal to delta t. Now it looks like I've written delta t prime there, and I'm going to have to make a quick change here. Okay, that's just delta t. So delta t prime will equal delta t if v is equal to 0. That's easy to see. Now if v goes up to 0.9 c, 9/10 the speed of light, and of course that's not an easy velocity to attain, but if we could attain that velocity, the delta t would increase to 2.3. I'm sorry, the delta t prime, the time that we measure, would be 2.3 times as long as the delta t measured in the lab that's passing by us. At 0.99 c, we would get 7.1 times the delta t. Now how do we get these numbers? If we put in 0.9 c, if v equals 0.9 c, we just put in 0.9 c here, square it, and divide by c squared. We're going to get a 0.81. 1 minus 0.81 is 0.19. Reciprocal of the square root of 0.19 is 2.3. I said that fast, but it's just a matter of plug this in for v and do the rest. We see that as we get closer and closer to c, this multiple gets greater and greater. If we're within 1/10,000th of the speed of light, off by just a 10,000th, then we're going to have 71 delta t. That means that the time intervals that we measure, the delta t primes that we measure, will be 71 times as long as the delta t's measured in the lab. Now, it's not just light beams, of course, that give us these results. Any time interval measured in the lab will be longer by the appropriate factor when we measure it while in relative motion to the lab at various speeds. Okay? Here we have a sample calculation for the 0.9 c, the one I went through quickly just by saying it, but we plug in the 0.9 c. The c over c squared gives us just the 0.9 squared, and we get the 0.19 here, the 0.43 here, the 2.3 here. Just illustrating the substitution. I'll also comment that if we measure the force required to accelerate the lab as it goes by, that force is going to be greater by the same factor, depending on the speed of the lab. The force is going to be greater than we would expect for the acceleration that we get, meaning that the effective mass of the lab or of any object that's moving at a large speed relative to us increases. We also note that the length of anything in the lab will shorten by a factor that's equal to the reciprocal of this. In other words, at 0.9 c, everything will get 2.3 times shorter, or 1 over 2.3 times as long. Okay, you can read about these things in your text, but these ideas follow fairly easily by geometric arguments. And I'll also mention, finally, that simultaneity is not preserved. If two things happen in that lab at two different points, and if they're simultaneous as measured in the lab, they won't be simultaneous as we measure it if we're moving at any non-zero velocity with respect to the lab. And that non-simultaneity becomes more and more easily observed as our speed increases.